So today I'd like to talk about anti-symplectic involution and Floer cohomology. This is a joint work with Kai and Ono. So let M be a symplectic manifold, and tau is anti-symplectic involution. This is by definition is tau is involution, and pullback of omega by this involution is minus omega. This is the definition of anti-symplectic involution. Now, today, so typical example of anti-symplectic involution is complex conjugation of complex projective space, and I think more interesting anti-symplectic involution will be discussed Jake Storm's talk, I suppose. So today, so if you have a anti-symplectic involution, then a fixed point set of this involution, if it is not empty, gives some example of a Lagrangian submanifold. So today I like to talk about Lagrangian Floer theory for the fixed point set of anti-symplectic involution. So now I think it is well known that Lagrangian Floer cohomology for general Lagrangian submanifold cannot be defined in general. But we studied and established some general theory of obstruction to define the Floer cohomology. And yeah, so our book is now on sale, so please buy our book. Okay? Anyway, however, even though the general foundation of general obstruction theory or deformation of Lagrangian Floer theory, it is hard in general to find which Lagrangian submanifold is unobstructed or obstructed. So today I like to discuss this problem for this fixed point set of anti-symplectic involution. Now, here is one of the main theorem. So now let M be a symplectic manifold, a closed symplectic manifold. And L is a fixed point set of tau. Tau is anti-symplectic involution. And assume L is oriented and tau relatively spin. I explain the definition of tau relatively spin. And moreover, we assume C1 of Tm evaluated phi 2m is divided by 4. Or C1 Tm evaluated by 2 is even and pi 1 of L inject to ambient space is inject. Then, as a fixed point set of anti-symplectic involution is unobstructed. Unobstructed means that okay, namely we construct a filtered infinity algebra associated to a Lagrangian submanifold, and we also define some infinity version of Molar-Cartan equation. So this is a set of the solution of Molar-Cartan equation. This is then unobstructed is by definition is the set of there is a solution of a Molar-Cartan equation. Then using this solution, you can deform the infinity algebra so that Floer cohomology of L can be defined. Okay. This is the first theorem. And moreover, if assume C1 of ambient space is exactly equal to 0. For example, if you consider the Calabi-Yau case, then of course this implies this assumption L is unobstructed. Moreover, we can show that the Floer cohomology of this L deformed by any Molar-Cartan solution does not vanish. This is the second theorem. So in particular, L is non-displaceable. Under Hamiltonian diffeomorphism.
So is it isomorphic to the single cohomology?
No, not in general. I will explain some example if I have time. So there is one remark, an important remark. Actually, these results we wrote some preprint and put in the archive. But in the archive version, the assumption of theorem 1 is not correct. So
Why don't you change?
I'm sorry. I'm now revising, but very, very sorry. So in the archive version, the assumption is stated as assumption of in theorem 1 is stated as C1 just the even. Then you can find a counter example very easily. For example, this is the most simplest example. So RP1 in CP1. Okay? Then in this case, Maslov, no. C1 is, of course, even. But I mean, unobstructedness is in strong sense. So RP1 is in that sense not unobstructed. I mean obstructed. This is weakly unobstructed. But in a strict sense, RP1 is obstructed. This is a counterexample of this.
Do you expect that it's always weakly unobstructed? I mean, if I take C1 that's even, and I take a real locus, should it be weakly unobstructed? Always? Or, I mean, I don't know.
Yeah, I don't know, because we have to analyze some weak solution in the reflection, so it's not clear.
Can you say quickly what weakly unobstructed means?
Yes, but yes.
If it's not
If I have enough time, so sorry. Yeah, some people know the potential function. Then I can say something. So in this case, the value of a potential function is equal to 0. But in the weakly case, in some sense, not equal to 0.
Just for you. So M0 is a multiple of the n. That's what you think.
Okay. Now, so to prove this theorem, the key ingredient is a careful study of orientation. Orientation modular space of holomorphic disk. So now I'd like to explain what is the tau relativity spin structure. So relative spin structure and tau relativity spin structure. Now, in general, you have a Lagrangian submanifold L, and I assume this is oriented. If you consider the non-orientable case, please contact Jake. Okay, but today I assume that this is oriented. So now L is relativity spin is the following. The definition is the following. There exists a class of ambient space such that W2 TL equal to a restriction of this class. This is the definition of relative spinness. Then, if Lagrangian submanifold is relatively spin, then the modular space of holomorphic disk with Lagrangian boundary condition is orientable. But to prove this theorem, we have to analyze the orientation. So orientability is not enough for this study. So I have to explain relative spin structure. So now I'd like to explain relative spin structure. Relatively, I'm not sure. So if your Lagrangian submanifold is L is relatively spin, then you have some class ST. So then ST, class ST gives some vector bundle on M. So this is oriented real vector bundle such that W2 of V is ST. Strictly speaking, we have only there is a V exists on 3 skeleton of this M, but anyway, you have oriented real vector bundle. So by this assumption, W2 of V, TL plus V restricted to L is equal to 0. So you have a spin structure on TL of this bundle. So I denote this spin structure on sigma. The spin structure means somehow trivialization on this bundle on 2 skeleton. Okay. So if you have your Lagrangian submanifold relatively spin, then you have a real vector bundle V and spin structure sigma. So that W2 of V is ST and sigma is spin structure on TL plus. Okay. So I call this relatively spin structure. Okay. Of course, the choice of V, there is many choice of V. So we have to introduce some equivalence relation of this set of relatively spin structure. So here's the definition of equivalence relation. So if you have 2 relatively spin structure, and we say these spin structures are stably conjugate. If and only if there is a Ki, this is an integer, and there is a phi, and this is a V1 plus this is a trivial vector bundle of rank K1, and phi is orientation preserving bundle isomorphism, such that the induced map, how to say, identity plus phi. This is a bundle map from TL plus V1. Also, yeah, since so in this factor you have a spin structure sigma 1, and on this factor you have a trivial canonically trivialization. You have a canonically trivialization. So this trivialization sent to sigma 2 plus identity by this boundary isomorphism. So this is a sort of a stabilization of the spin structure.
How is defined before restricting to L? But
I see. But here, yeah. Yeah, strictly speaking, you are right. So yeah. Okay.
You would like to say standard instead of
Ready?
standard instead of item. It's completely.
One. How to write? Anyway, identities are not correct. So
sigma k underline, sigma k1 underline.
just canonically choose. So now we put spin ml is relatively spin structure divided by this stably conjugacy relation. So this is a set of stable conjugacy class of relatively spin structure. Then, if you choose this class, then we can define an orientation on this on the modular space of holomorphic disk. So, and also we can show the following proposition. This is our book proposition. Okay. So there is an action of relative cohomology to this stably conjugacy class. This action is simply transitive. So there is a simply transitive action of this cohomology on this space. So you can identify the set of relatively spin structure as a stable conjugacy class of relatively spin structure with this relative cohomology. Today, we don't need a precise description of this action, so I skipped the definition of this action. But I want to say the following proposition. So, if you change the choice of a relatively spin structure, the orientation on the modular space might change. Then we can describe the change of the orientation on the modular space by using this action. So the following proposition describes the change of orientation on the modular space by changing choice of relatively spin structure. Sorry?
The modular space is smooth.
Which modular space?
Pin.
Just a set.
It's a vector space by the simple transitive.
Okay. If you know a usual spin structure, then you forgot there. Then the set of the spin structure can be identified as. So now, yeah. So let X is the element of relative cohomology class. Then and beta is a relative pi 2. So you have modular space of holomorphic disk. With class beta. And as I said, if you choose a spin structure, a relatively spin structure, a conjugacy class of relatively spin structure, then you have some orientation on this space. And yeah, but if you change the relatively spin structure by this action, then you might have another orientation. So this map is identity map, as I said, but this map is orientation preserving, if and only if x beta is equal to 0. This preparation is also obtained by Cho. So we can describe the dependence of the choice of the spin structure by this proposition. Okay. Now, so far, this is a general story of orientation on the modular space of holomorphic disk. Now, we come back to the situation of anti-symplectic involution. So now, tau is involution. And L is a fixed point set of a relatively anti-symplectic involution. Then we can define the map induced by tau, denoted by tau star, between the set of relatively spin structure by following. So you have a relatively spin structure, then you can take a pullback of this bundle and pullback of spin structure. Okay, this is because L is fixed by this involution, so we can define this map. Now, I define the tau relatively spin structure. So relatively spin structure V sigma is a tau relatively spin structure if and only if the pullback of this spin structure is stably conjugate in the original one. Okay. This is the definition of tau relatively spin structure. So if a Lagrangian submanifold has a tau relatively spin structure, then we say L is a tau relatively spin. So I'd like to show you some example of tau relatively spin Lagrangian submanifold. Example. The first example is a case of L is a spin manifold. In this case, L is automatically a tau relatively spin. This is because, so if L is a spin, then you have some spin structure. So okay. Then tau is of course is identity on a fixed point state. So tau preserves this spin structure. Moreover, if L is a spin, then we can take class ST is equal to 0 and V is a trivial one. So relatively spin structure, that is a spin structure on this bundle. So on this factor we have a spin structure, and on this one is a trivial one. So so it follows that tau preserve this spin structure, relatively spin structure. Okay. So in this case, tau relatively spin structure. This is most important case. So, for example, let us consider the case of a real projective space. So now we are considering an oriented case, so we consider odd dimensional case. So in this case, W2 is X is a generator, the W1 of a hyperplane bundle. So this is so RP 4n plus 3 is a spin. So this case is a tau relatively spin. But when n is even, then this is not a spin, but we can show that RP 4n pi plus 1. So n is greater than or equal to 1. So RP1 is a spin. So this is not tau relatively spin. This is a very elementary example. So in theorem 1, I want to check theorem 1 by this example. So let us consider the case of dimension 4n plus 3. Then in this case, Lagrangian is a tau relatively spin, and C1 of Cp divided by 4. So Rp unobstructed. But this fact is can be proved not by using theorem 1, by using Yongin's earlier work, because in this case this is a monotone Lagrangian submanifold, and the minimal Maslov index is equal to, so if so actually in fact so 4n plus 4 is greater than or equal to 3. So in this case, this follows. This means from Jung's earlier work. So I can say that it is better to use or apply the theorem 1 for the case of non-Fano case. For example, Calabian case or non-Fano case. In the Fano case, we can prove unobstructedness for other more elementary methods. Anyway, we can check theorem 1 by this example. Okay. RP1. RP1 is a spin, so it's a tau relatively spin. But so C1 is even, but pi 1 is not injected. So the assumption of theorem 1 is not satisfied. This is a revision of our work. So now I like to discuss orientation on the modular space and anti-symplectic involution more precisely. So anti-symplectic involution change relative homotopy class of disk. For example, you consider the two sphere, and you have a upper hemisphere and the lower hemisphere, and you consider the involution of tau. Then the homotopy class changes. So in general, tau preserves. Does not preserve a homotopy class. So we proceed as following. So let us consider the following quotient space, quotient set. By L. This is equivalence relation is given by B. The same symplectic area and same Maslow index. Then tau preserved this element because tau preserved the symplectic area and Maslow index. So now we consider the following modular space or M. So I'm sorry, I forgot one thing. So we take J, almost complex structure compatible with omega, and assume that J satisfies the minus J. So tau anti-invariant complex structure. And consider modular space Mj beta. This is a union of B. B is element of pi, relative pi 2. Okay. Then we can define the induced map tau star on this modular space. No. By following. W Z is this is a module of a disk, or holomorphic disk, and a bar is a complex conjugation on the domain. Okay. Then you can easily check that the tau star defines the involution on this modular space. This is the induced map on the modular space. Now I like studying how this map respects or does not respect the orientation on this modular space. Yeah. Moreover, let me introduce modular space with a marked point. So mk plus 1 mj beta is a so mk plus 1. Yeah, so this is I denote by w z0 zk and z1 plus. So k plus 1 is a number of boundary marked point. So the picture looks like this. So here is a marked point on the boundary, and there are some other interior marked point, and map to ML W. Okay. Then we define the induced map tau star on this modular space by following. W is given by this one, and take a complex conjugation on the boundary, on the marked point. Okay. So I like to note that this map does not preserve cyclic ordering on the boundary marked point. So Z0, Z1, Zk. If you put cyclic ordering on the boundary marked point, and then tau star maps to something like this. So if you choose a counterclockwise ordering, then after that, the cyclic ordering on the boundary marked point reverse. So when we construct the infinity algebra associated with Lagrangian submanifold, we consider some component of this modular space that is the main component of this modular space. That is that modular space consists of the holomorphic disk with boundary marked point, and so that the cyclic ordering on the boundary marked point, ordering of the boundary marked point is a cyclic order and counterclockwise. So we use the following modular space. Modular space to define an infinity algebra. Yeah, so Z0 K is counter clockwise cyclic ordering. So the tau star, this map does not preserve this main component. However, we modified tau star slightly. We can also define the map denoted by tau star main by Z0 bar and ZK bar, Z1 bar. So when we applied our orientation problem to the Floer theory or infinity algebra, we use this map tau star main also. Now the following proposition is a key proposition of the proof of the theorem 1 or theorem 2. So L is a fixed point set of involution, and assume this is oriented and with some relative spin structure. Not necessarily tau relative spin, but choose some relative spin structure. Then tau star, you can consider the map tau star, mj beta, and tau this map. So if you choose a relative spin structure, then you can consider the oriented modular space by this spin structure. And you also consider the pullback of this relative spin structure and the oriented modular space by this pullback spin structure. Then tau star naturally define this map. Then we can show that this is orientation preserving if and only if mu beta is divided by 4. Okay. This is a key ingredient of the proof of the theorem. So in particular, if you choose a relatively spin structure you choose is a tau relatively spin, then this is the same one. So in this case, tau star is just a same map, and in this case, yeah. In particular,
Tau is the main or
tau star.
tau is the main or tau is
No, not the main. There is no marked point so far. So, then this is the same modular space with the same orientation. Okay. So when we consider the marked point, then we can show the following by the similar argument. Tau star this is still the case, not the main component. Preserve. So complex conjugation, we take a complex conjugation on the marked point. So the complex conjugation is orientation reversing map. So we have a k plus 1 marked point, boundary marked point, and the interior marked point. But both of them we consider the complex conjugation. So we have to put this number. So I'd like to discuss some application to the Floer theory. Yeah, I think 10 minutes. I have 10 minutes. So, yeah. Roughly speaking, we construct infinity algebra starting from a relatively spin Lagrangian submanifold, a compact Lagrangian submanifold. We construct infinity algebra so that, yeah. So, yeah. MK, K is 0, 1. CL is a smooth singular chain of Lagrangian submanifold with the coefficient some Novikov ring. And MK beta is defined by, roughly speaking, the following. K plus 1 to J beta taking a fiber product on this Lagrangian submanifold with a smooth singular chain. with Q coefficient. And you have a evaluation map at the zeroth marked point. This is some fiber product on the modular space with a singular chain. So picture looks like this. You have at the first marked point, then the disk attaches P1 at this point, and so on. And the class of holomorphic disk is beta. And then you have an evaluation map at Z0. Then you have some chain of this Lagrangian submanifold. And summing up MK beta by beta, then you have a operation, infinity operation of MK. So this is the rough story. So satisfy the infinity relation. Now, so let us consider the case when L is a fixed point set of anti-symplectic involution. Then we can show the following. If the fixed point set is a tau relatively spin, then we can show that MK beta P1 PK satisfy the following equality. No. So ordering of P1, PK converse. So where epsilon is given by the following k plus 1 plus m plus k. Sorry. Yeah, sorry. There is no interior marked. Degree P is a degree of P as a cochain. So geometrically P has a dimension. So N is a dimension of L. This is a formula. Okay. So yeah. So using this formula, let us consider the case when k equal to 0. Then we can obtain some unobstructedness, the proof of unobstructedness. So in this case, M0 beta 1 is 2 mu plus 1 M0 tau star beta 1. Okay. So if mu, a Maslov index, is divided by 4, then this number is odd. Therefore, these term, the sign on this, the coefficient of this term are converse, opposite. So M01 is by definition summing up beta of M0 beta 1. This is the definition. So if this equality holds, then you have some cancellation. So this is exactly equal to 0. So this implies.
You have put some formal parameter in the sum?
You are right. Yeah. But I never explained Novikov ring, so sorry. Some parameter. I put some parameter. So this implies that 0 is a solution of a Mohr-Cartan equation. Actually, Mohr-Cartan equation is defined by MEB M01 plus M1B plus M2B B equal to 0. So ME0 equal to M01. So this implies that M01 equal to 0 is implies that 0 is a solution of a Mohr-Cartan equation. Two? No. Two. Then we can show that put P, Q, how to say, minus degree, no, PQ, not X, Y.
In this proposition,
Yes,
do you mean tau star beta or minus tau star?
tau star beta.
Then this area is
The same one. So cancellation occurs.
anti-symplectic.
No. Yeah. The same symplectic area. So the coefficient they cancel out. Okay, so I introduced by L. So the same one, but so RP1 case, this number is even. So each disk contribute on MK operation M1. That is the potential function M0. But for example, RP3 case, these disks satisfy this equality, so it's cancelled out.
Floer is just saying that if you take the class beta,
Yes.
then the integral of omega over it is positive. Which
Yeah. Sure.
But that implies that the integral over tau star beta is negative because tau is anti-symplectic.
No. We take a J anti-symplectic.
The W tilde is the conjugate on top, both on
Yeah.
domain.
Yeah.
And it's still positive.
The tau star beta though is minus tau. Wait, and somehow it's minus tau star beta. And instead of sense of cohomology or like induced map on relative pi 2, it's not that map. It's the map where you also put minus.
It's just I think it's question.
Minus.
Yeah, it's a mess.
The naive interpretation of tau star beta would give you a class in which omega is negative.
I'm sorry. Yeah.
Okay, your definition of tau star is not the one we have in our
I think.
Yeah, exactly.
D.
You
not
definitely
the usual tau star.
exactly. Okay.
It's the map of
Okay,
cohomology.
yeah, you understand.
We have
No. Sorry. Yeah, I have to stop. Yeah. So just one more point. So if you consider case k equal 2, and I defined a product structure switch by this sign. That's right. 2 beta. Then this define is how to say dx so this product structure defines a graded commutative product. Okay. This is followed from this formula. So if you consider the case diagonal manifold in a product symplectic manifold, this is a fixed point of anti-symplectic involution. Then in this case, this product structure defined by Lagrangian Floer theory on this diagonal is coincided with the quantum product of this absolute symplectic manifold. This statement follows this observation. Thank you.